This is FE Peer Review. The date is January the 4th, 2024. Bev and Paper struggle with straight and curved lines. I hope this helps. Where's Wally just put out a video. It was looking at a live stream done by Bev and Paper. They were looking at the issue of the Great Circle, and they were questioning some things about the shortest path between two lines. This is Where's Wally's video, and I've put a link in the description. This here is Bev's video, Bev and Paper. They're on a channel called PD194, and they're discussing a sphere and the Great Circle. And to clarify things, Bev left this pinned comment. For clarity, Paper and I were discussing the modus tollens laid out by Bob the Science Guy in his infamous Flat Earth Logic video. His argument goes like this: if and only if the Earth is a sphere, then the shortest distance between any 2 points in any direction will be a great circle distance. And then Bev added on, I see that you are doing your best to support your superiors, but the straight line will always be the shortest distance between any 2 points in reality. I responded to Bev with a brief comment. I'm going to do a small video response that avoids math and just shows some basic geometry concepts about planes and the Great Circle. I hope that will help clarify why the Great Circle is in fact the shortest path on the surface, and I emphasized on the surface, of a sphere between any 2 points. Conceptually, it's pretty simple, and if we can grasp that, we don't need to look at a lot of complicated math. So I've done that in a small SketchUp model, which we'll look at next. Let's start on the left here. We're looking top down. We're going to be looking at this in 3D as well, but we're going to start by looking top down. At the bottom, I've got a line. I've drawn that line arbitrarily at 1,000 meters. If you see that little tape measure symbol, that indicates 1,000 meters. Also, I can select the line, and in the upper right corner of the screen, SketchUp has a window that says Entity Info, Edge. It calls lines edges, and it gives me the length of the line. So what I did was I then copied that line several times going up the image here, and then I bisected that line at its center point with another perpendicular line, and each of them gets longer and longer, and I use those to construct the arcs. So each arc starts at one end, ends at the other, and touches that bisecting line. That means that each of these arcs, this would be what's called a chord length. Each of the chords on these arcs is exactly the same length. They're all 1,000 meters, just like our first line. There you can see the tape measure 1,000 meters. Now, just by looking at this, now Bev said something that gave me the impression his intuition was failing him. And this is something that happens to all of us at times. We think there's going to be a certain result, just intuitively. We just sort of sense there's going to be a certain result. Then we actually look into it more carefully and we discover the result is not what we expected. Sometimes it's even the opposite of what we expected. So I think Bev's intuition was failing him at one point. I heard him say something that gave me the impression he was getting confused about chord lengths and arc lengths. What he said sounded like he was assuming that a longer arc length, a longer path, would have a larger diameter. Longer path, larger diameter. Sort of sounds right, you know, a longer line and a larger shape or whatever. But in fact, it's the opposite. If we look at these arcs here, we can see that each arc starts and ends the same distance apart, 1,000 meters. The bottom arc, this one here, it has a very large diameter. And then the diameter gets smaller and smaller with each arc. I made the top arc a complete semicircle, so its diameter is equal to, you can see those three dimensions are all the same. So this top arc has the smallest diameter, and this bottom arc has the largest diameter. However, the top arc clearly has the longest path between the two endpoints, which means the longest arc length between the two endpoints, whereas the bottom arc has the shortest path, or shortest arc length between the two endpoints. And we can confirm that if we look at the upper right corner where we have the entity info Now I've got the bottom arc selected. It says arc. It gives me the length of the arc, 1026.46 meters, and a radius, 1300 meters. Whereas the top arc has a much longer path, 1570.8 meters, and a smaller radius, 500 meters. So I think that was one point that Bev just kind of like rushed through and didn't really stop and fully work out. The longer the path, the smaller the diameter. And this is going to play into the great circle path on a sphere. Now I'm going to shift to a 3D view here. And what I've drawn, I want to cover another point here, and that's that 3 points that are not collinear, in other words, not on the same line, define a plane. 2 points do not define a plane, but 3 points define a unique plane. Now, I've created a little graphic down here, a sort of a symbol, and all I'm intending to do is show 3 points, so the center of these 3 circles, and I wanted to show that they're not on the same line. However, they are on the same plane. And then off to the upper right, I've created a plane. And I'm going to move a copy of this plane over here so that it sits nice and tight with those 3 points. And we see that all 3 points are on the same plane. Now, I cannot create a different plane. I can scale this one, of course. I can make this particular plane bigger or smaller, and those 3 points are still on it. But I can't create a completely different plane that also passes through those same 3 points. And just to demonstrate what happens, here I'm going to rotate a copy, and the 2 endpoints there that we saw, those are still on this new plane, but we've lost the middle one. This one is no longer on this new plane. So this new plane does not share the same 3 points. It only shares 2 points. I'll do another example here. In this example, we see that the middle point is on the same plane as the original plane, but only the middle. We've lost the points on either side. So that's a basic geometric fact. And my goal here is not to try to prove these things. All of this stuff can be proven mathematically, but my goal here is simply to present these geometric facts in a way that's we can grasp them intuitively and not have to rely on the math to grasp them. Because I know Bev may be like me. Many of us find it easier to understand this stuff if we get it visually. That's why I ended up doing architecture and structural engineering at university instead of going into something more abstract like physics. I'm more of a visual person. So there we have 2 concepts that will be useful to us. The arc length relative to its diameter, and that a plane is uniquely defined by 3 points. We can take that to a sphere, and I've made a sphere over here. There's our sphere. And I put some planes through this sphere here. I cut some planes through it. And let me show you, just do a brief recreate that roughly. So you see that plane that I copied over from the left to the right cuts through that sphere. We might call that the equator. It's cutting through the sphere at the point where it creates the largest possible slice. We can't slice through that sphere in a way that gives us a bigger slice. So I created some other slices further up, going up here. There's another one, and one at the top. And in fact, I laid them out so that if you imagine that they were latitude lines, this would be the equator. This would be 22.5 latitude. This would be 45 latitude. And this would be 67.5. So that's how I divided it up. And as you can see, as we slice through the sphere, each circle gets smaller and smaller. In other words, the radius of each circle gets smaller and smaller. I'm going to do a top-down view, and I'm going to get rid of the perspective. So tie this idea back to our original concept, which was that the shorter the path between the two lines, the larger the radius. If we go back to our stuff on the far left here, the shortest length of curve has the largest radius. Bev said that the shortest path between 2 points is a straight line. And, well, yeah, in a sense, that's true. Very much. But that wasn't what the great circle's all about. The great circle is not about the shortest path between two lines. It's about the shortest path on the surface of the Earth between 2 points. So I'm going to define a point A and a point B, 2 points on our path, on our surface, that we want to find the shortest path between those 2 points. I'm going to add that to our model here. Okay, I've added 2 points. Now you'll see two sort of tick marks. One where I've got the mouse and the other where I'm circling the mouse. Those two, where those two little lines meet that circle, that's the surface of our sphere, and that's at the 45 latitude mark. So we'd like to know, based on staying on the surface of the sphere, what is the shortest path from one of those points to the other? Is it simply following a line that right along the latitude line? Is that in fact the shortest path? Or is there some other path staying on the surface of the sphere that's shorter? Now, of course, we could draw a straight line between the two, and that would be the shortest possible path. However, that would not stay on the surface of the sphere, and I'll rotate this around so you can kind of see how it goes inside the sphere. So if you were to start at point A over here and dig a tunnel that gets deeper and deeper and deeper, and then to the halfway point, and then gradually dig your way back out to the surface at point B on the left, that path would in fact be the shortest path. But that's not a path that keeps you on the surface of the sphere. And that's what the great circle is all about. So if a straight line is not an alternative that we can use because that doesn't stay on the surface of the sphere, that requires us to dig a tunnel, then we want to find the shortest path on the surface. That means that we want to have the path that has the largest radius, because if you remember from what we did on the upper left of the screen here, the larger the radius, the shorter the arc length. So we want to find the largest radius that we can put on our sphere that will connect those 2 points. Go back in here. And what we saw when we did these, when we cut these sort of latitude planes here, was that the biggest one we could make was equal to the equator, was equal to the radius of the sphere itself. We couldn't make one any bigger than that. We can't create an arc that has a radius bigger than the sphere itself and have it sit tight on the surface. So let's go and take a look in here and see if we can make a copy of this one, which is our largest radius, and use it to connect the 2 points that we are interested in. I'm simply going to move a copy out to the side for the moment. So what I've done here is I've taken that largest circle, that equator circle, and I've copied it up to the level of 45 north latitude, and I've had it intersect those 2 points, our start point and our end point. And of course, I haven't quite solved the problem yet because it's going inside the sphere. But I can rotate this thing so that the third point that will define the plane of that circle passes through the center of the Earth. So I'm going to do that next. So as you can see, I've rotated that circle, keeping it passing through those starting and end points on our surface. So it passes through the same start point and the same end point. And I've placed it so that it also passes through the center of the sphere. And that circle that you see highlighted there is the same size as the one that we have at the equator. It's the largest we can make. So it's got the largest radius of all the circles you see here, and the largest radius that we can actually put on that sphere. And if we go back as a reminder and look at these, the largest radius has the shortest arc length, or the shortest path. So what we get is one path following the latitude line that goes from point A on the right side straight across to point B on the left, and the other path starts at point A on the right, but it follows a larger radius and therefore a shorter arc length. So we'll want to measure those two and actually check and see if what I'm saying is correct. So we'll do that next. Now, the easiest way to get those lengths off of SketchUp is to draw some new arcs, but they'll start and end the same way. So start at one end, go to the other. And so there's our first arc. That's the one that follows the latitude line, highlighted in blue. And if we look in the upper right corner under the entity info section, it says arc. It says it's got a radius of 353.39. And it's got an arc length of 555.43. Now we'll draw another arc that starts and ends at the same places. There's our second arc. It has a radius of 500 and it has an arc length of 523.57. So 523.57 versus 555.43. So as we see, the arc following the larger radius has the shorter path. That is a geometric construction that shows the great circle. And that's why it's shorter to depart from your latitude line. If you were starting at 45 north latitude and then ending somewhere else at 45 north latitude, your shortest path would not be to follow your latitude line, but rather to follow the line that I've got highlighted. And I'm going to show you another quick and dirty way to see that. Here's a little website called AeroSavvy. They did this little exercise. It's one that you can find all over the internet. This was just one of the first ones to come up on my Google results. I'll put a link in the description. They give a whole little discussion of what Great Circle navigation is all about. But they show this little exercise, and Bev, you can do this. This is very easy little exercise. Get yourself a globe, a little desktop globe, and a piece of string, and then pick 2 points that start and end at the same latitude. It doesn't have to start and end at the same latitude, but for this exercise, I think that would be the best comparison. And you take one end of the string, let's say it's under the right thumb here where I'm circling the mouse. You hold the string there nice and tight, and then to the surface of your starting point. And then you take the left end of the string and you pull it over to where you're going to end. And if you just keep pulling on the string, holding the right end so that you can pulling on the left so that it gets tighter and tighter, you can get the string nice and tight to the surface, and you get it to the point where you can't make it any tighter than that. And if you do that, you're going to find that it does not follow a latitude line between those 2 points. It follows a different path, like the one shown in the picture, the one shown in our model. that's really all the evidence you need that the latitude is not necessarily the shortest path. If you happen to do this on the equator, it will actually follow the equator. If your start point and your end point are on the equator, then it will stay on the equator, your string. Also, if you do it and you stay on the same longitude line, so if you do a north-south path, starting on the same longitude and ending on the same longitude, it'll stay on the longitude line. But if you do it across a latitude line, or if you do it just between any two random different spots, you're going to find that that's a simple way to get your great circle. So Bev, there you go. Play with that a little bit, and I think maybe it'll become more clear what's going on there. You can see quite clearly that it deviates, the string deviates from the latitude lines. The rest of you watching this, I hope you enjoyed it. I'm sure there's nothing much too new and groundbreaking here, but that's not what my channel's all about. It's more about just trying to explain things as best I can. Anyway, I hope you liked it. If you did, please give it a thumbs up and do subscribe if you haven't already. Thanks. Have a great day.